So my name is David Delabassee. You can find me on Twitter at Delabassee. I work at Oracle in the Java platform group. So basically, our group is responsible for Java and OpenJDK. I live in Belgium, but I'm reporting directly to the group in the US. Despite my French accent, I'm not French, but I'm from the French-speaking side of Belgium. So I work at Oracle, so this is the safe harbor statement slide, so please read it carefully. Thank you. This is my personal disclaimer. So if you follow the news, you might have seen that Apple has launched a new MacBook 3 days ago. And the big thing about that new laptop is basically the new keyboard. Unfortunately, I'm using the old one with the butterfly keyboard, and there are clearly a lot of issues with that keyboard. It has been fixed many times, but it still doesn't work. And I'm using one of the early versions. So today I'm going to do a few demos. If any of my demo fails, it's not my fault. It's due to the broken keyboard that I'm using. And I'm serious about that. So, very quickly, who is using containers today? Just by show of hands. So yeah, quite a few people. That's what about. So what is a container? So basically a container is a way to package a software and its dependency into a standard unit that can be easily shared and deployed across environment. There are multiple runtimes like Docker, Creo, Alexi, Runc, and so on and so on. So today what I'm going to use Docker. And if we look what Docker use, Docker relies on Linux features such as cgroups and namespace. So basically what I'm going to discuss today will apply to any container that relies on cgroups and namespace. A container is not a virtual machine. Basically, containers rely on the host operating systems. And that basically means that in a containers, you have the same operating system that you have into your underlying host. On the opposite side, we have VM, which provide a stronger isolation because they rely on an hypervisor. So that means that you can have a different operating system than the host, than what you have in your different VM. In between, we have, well, one of the one of the benefits of VM is that they provide a really strong isolation. So you don't really have that isolation on the container side. On the other hand, VMs are pretty expensive. They are slow to start and so on. In between, we have what we call kata containers, which are basically lightweight VMs. So I'm really going to focus on containers today. Now, I'm using a Mac, so that basically means that to run Docker on my Mac, under the hood there is a VM. So basically I have a VM that is running Linux, and in that Linux I have multiple containers. So if you are using Docker on Mac, you are using container within a VM. So, Java. Well, if we look at the adoption of containers within the Java space, it's pretty good. There are multiple reasons for that. So the first reason is that if you are going towards cloud deployment, well, containers is kind of givens. If you are using Kubernetes, it's a given that you have to rely on containers. But also, if you look at the Java landscape, there are a lot of tools and a lot of frameworks that basically helps you to use containers. We have multiple Maven plugins. We have JIPs that helps you to easily create containers, and so on and so on. If you look at the different microservices frameworks that we have in the Java space, such as Helidon, Quarkus, and so on, they have all out of the box the ability to create containers out of your application. So it's basically very trivial to rely on containers. And then there's the serverless space. If you look at the serverless space or the function as a services space, all the solutions that we have that support Java are basically relying on containers. So at the end of the day, it's a given that you will have somehow to rely on containers, whatever you are doing. So, JVM containers, what do we expect? Well, we basically expect two things. So first of all, the Java virtual machine, whenever it runs in a container, should behave as a good citizen. What we mean by that is that the JVM should be aware that it runs in containers, and we will discuss why it's important. And then there's the discussion about the latency. Given that you're going to use a lot of containers, you will start a lot of containers. And obviously, you expect those containers to start as quickly as possible. And if we look historically, Java has been designed for long-running application. So Java is nearly 25 years. And back then, when we were starting a Java server, it didn't really matter if the server took like 5 seconds or even minutes to start, because you were only going to start that server once and it would run for days, weeks, and months. Now, we're a different world where basically containers are disposable. So you will start a container and you will quickly kill that container to start a new version of that container. So startup time is something which is very important. So let's have a very quick hello world demo of containers. So the first thing that I need to do, so I just got that 2 hours ago. So Docker wants to update itself. Obviously, given that I'm going to rely on Docker for my session, I will do that after my session. So let's see. MSQ. So I have a simple Docker file. So it's a very trivial application. So what I'm doing here, I'm picking a Java image from java.latest. I'm creating a directory. Then I'm copying. I'm putting in my Java source into my container. I use Delabassee to compile that. And finally, I run the applications. So if we look at the application itself, it's a pretty basic application that basically looks at some environment stuff, such as am I running in a container, which Java virtual machine I'm using, and so on. So let's build that very quickly. So build T, and let's call that MSQ. Docker run MSQ. So this is our Java application running into a container. So it's pretty basic. You see that I'm not using a recent version of Java. I'm running indeed in a container. I have 3 cores, and my command function join pool is configured at 2, and so on and so on. If we look at the size of this application, at the Docker image of that application, it's over 600 megabytes. So that's an issue when it comes to startup time, because this is super heavy, and obviously my application is very basic. So there is a mismatch there that we're going to discuss later. So that's basically how it works. So let's quickly go back to the slides. So the first thing that we're going to discuss is latency. How can we improve the startup time of our containers? There are 2 levels on which we can work on. First, there is the container level, and once the container is started, there's the Java level. So let's first quickly discuss about the first level. A container is basically made up of different layers. For a Java application, we have 3 types of layers. We have the operating system layer, we have the Java runtime layer, the JRE, or the JDK layers, and then we have the Java application itself with all its dependency. And the basic idea is that we want to reduce as much as we can the size of those layers, so that each time we need to start that containers, the container runtime has less bits to load from the registry. So top to bottom, at the Java layer, so at the Java application itself, we can only give best practices. So for example, watch out about the dependency that you're using. Watch out about the transitive dependency that you might bring into your code. Those kind of things. But at the end of the day, it's really up to you, the developers, to check that and make sure that that layer size is as small as possible. At the Java runtime layer, there are things that we can do. In Java 9, we have introduced modularity within the platform, and with that come JLink. So JLink is a tool that allows you to create a custom runtime Java for your application. The idea with JLink is that it's basically, it will create a runtime that will only carry the modules that are needed by your applications. So to give you some idea of the benefit that we can get using JLinks, I started from a whole JDK. So JDK 13, it weighs nearly 320 megabytes. That's a lot to run a small applications. So the next thing I did, I create, using JLink, a custom image that carry all the modules. That's a very stupid idea, because I don't think that there is any way to create any meaningful application that would use all the modules from the Java platform. But still, if we do that, we go from 316 megabytes to 178 megabytes. So we already saved a lot just by using a JLink. But obviously, the idea of JLinks is to create a runtime that only carries the modules that our code needs. So if I'm doing that, for that given example, I will go down to 15 megabytes. So from 168 to 15 megabytes. So that's a huge benefit. We have the ability using J-Link to remove some information that might not be needed at runtime, such as either files, man page. We can also strip out some debug information. If we do that, we will save another 6 megabytes in that specific example. We have two levels of compression that are provided by J-Link, and if we use compress 2, we will go from 44 megabytes to 34 megabytes. So basically, you see that by using J-Links, we are going from a full JDK that weighs more than 300 megabytes to a custom runtime that weighs only 34 megabytes. Now, something which is important to keep in mind is that we are doing that to reduce the size of the layers. Obviously, if we look at the two last options, given that we are introducing compression, that's induce decompression. So it might not be useful to reduce our layers using compression because we might pay that at runtime, given that we have to decompress the stuff. So that's what we can do at the Java runtime layer. The next layer that we can work on is the operating system layer. So we need to try to use an operating system that is lightweight. Alpine is a very good example. So Alpine is a Linux distribution that weighs around 5 megabytes those days. Now, there is an issue with Alpine. So it's a full-blown Linux system to run your code. Obviously, it doesn't have all the bell and whistle that you will get from a typical Linux distribution that weighs multiple hundred megabytes, but it has really everything you need to run your code. The basic issue is that Alpine is using Muscles. So Muscles is an alternative to libc, libc being the C library that the Java virtual machine use to talk to the Linux operating systems. And Alpine, unfortunately, use an alternative to libc. So we have this ongoing project, Project Portola, under the OpenJDK umbrella. And the goal of Portola is basically to compile OpenJDK on top of Muscles, so that you can use OpenJDK on top of Alpine distributions. So I have a demo to illustrate that. And the application that I'm going to containerize is the Minecraft server. Don't ask me why. Oops, sorry. So if I go here, let's see. I have this Docker file, and basically this Docker file, well, let's first build that to see what's going on. So Docker build -t Minecraft. So let's, let's run it, Minecraft. So this is the Minecraft server running into my containers. So it takes a bit of time, but that's really the Minecraft server that is, so Minecraft server is starting. Now let's kill that guy. Docker ps, Docker kill. That's not really the point. It runs. Let's have a look at the size of that container. So 100 megabytes. It includes everything to run the Minecraft server. So let's dive into that image. Dive Minecraft. So on the left side, we have the different layers that compose our containers. So on the right side, we have some details. So the first one, 5 megabytes, is Alpine. So that's the whole operating system that we need to run the Minecraft server. We have 181 bytes. That's this ULA text that is needed. Without that, it won't run. Then we have a config file, and then we have this 30 megabyte file, which is just the Minecraft. So basically, our code. That's the jar on the right side. And we then have this 60 megabyte layers. That's our custom runtime with all the modules and just the modules that are needed to run the Minecraft server. So basically, you see that by using J-Link and Project Portola, you can have a lightweight container image. In this case, we have an image that weighs only 100 megabytes that contain everything. That's the operating system. That's our code and the custom Java runtime. So Minecraft server needs 12 modules to run. Those are the modules that are needed to run. So using OpenJDK 13, we can have a custom runtime that weighs 88 megabytes. Now, if from those 88 megabytes you remove the debug information, you will save 14 megabytes. If you are using compress 1, you will save from the 88 megabytes, you will save 18 megabytes. And if you're using compression 2, you will save 31 megabytes. So that's what I had in my demo. I had a custom Java runtime that only weighed 57 megabytes. Now, in that specific example, if you remove the header file and the main page, you won't save anything, because I'm using the Oracle OpenJDK builds, and by default, they don't include the main page and the header files. Now, some cautions: if you are using Debian, if you are using the OpenJDK distribution for Debian, you might want to remove the native debug information. If you don't, your your custom runtime will wait with all the modules more than 500 megabytes, which is a lot. You just use the 12 modules that are needed by Minecraft, you are still around 500 megabytes. So you really want to remove the native debug from that specific Debian OpenJDK distribution. So, J-Link and Project Portola Alpine can be used to improve the startup time of the container. So what about the startup time of the Java layer itself? So this graph shows basically the startup time between Java 8 and Java 9. And unfortunately, smaller is better. So you clearly see that we had a big regression between 8 and 9. Now, I'm going to share a trick that we use internally at Oracle to improve the startup time of our Java application. And basically, we try to use the latest version of Java. You see that between Java 8 and Java 13, which is the current release, we have improved the startup time. Not only that, we have improved the startup time, but between 8 and 13, there are a lot of additional features which have been brought to the platform that you can use in your code. So that's an advice. Regardless if you are using Java in containers or not, try to use the latest version of the JVM if you care about the startup time. Now, something else which is quite useful is CDS, class data sharing. Anybody use CDS today? Okay, I see one hand. Anybody knows, except you, what CDS is? Well, let's say 5 or 6 hands. That's not a lot. That's not a lot because CDS is really not new. CDS has been introduced in Java 5, back then in J2SE 1.5, in Java SE 5. The idea with CDS is pretty simple. So when you start your Java application, you have your code, your bytecode, that needs to be basically transformed into an unary representation by the JVM. So the JVM needs to parse the class file format for your classes and do a lot of stuff to basically put that into something that can be used by the JVM itself. Obviously, you have more than one class. You have a bunch of classes. And that operation is quite expensive. So the idea with CDS is that the JVM will do that once, and once it has everything in memory, it will basically dump that to disk. And the next time your code will be started, that dump will be bring into memory directly, so that the JVM doesn't have to go through all those expensive operations again and again. So let's have a look at the benefit of CDS, what they can give us in terms of startup time. And for that, I'm going to use an Ubuntu box, because I need perf to basically show the benefits. So let's see. I have these, so let's have a look first. Which version of Java I'm using? Java 13, okay. So I have this same, let's see, hello world. I have this same application that basically shows some stuff. So this time I'm not running inside a container, I'm running inside a virtual machine. So let's compile that. And what we're going to do, basically I will invoke that application multiple times without CDS and with CDS, so that we can see what the startup time is without CDS and with CDS. So first, I'm going to skip CDS, so Xshare off. And I'm going to use this perf 42, which is basically perf invoked 42 times, so that we can have some average. So my application is invoked 42 times. And the average time to invoke that application is, the CPU clock time is 203 milliseconds. Now I'm going to do the same, but without CDS. Given that I'm using Java 13, well, the way to enable CDS is pretty easy. I just have to remove this guy, because CDS is enabled by default since Java 11, I believe. So from 203 milliseconds, let's invoke that. We can already see that it's a bit faster, just by the way it scrolls. So we went from 232 to 235. So if we do some quick map out of our heads. So basically, in that particular example, with CDS, I'm at 66% of the time it takes without CDS. So that's a huge benefit. That's a huge benefit because that's something that you have out of the box for free in the platform. And it's enabled by default if you are using a recent version of the Java virtual machine. So that's obviously something which is key when it comes to using Java in containers, but also outside of containers, because, well, that's something, I mean, reducing the startup time is important. Not only that, it will also improve the memory footprint of your Java application. So this tweet is from Charles Nutters, and basically, well, he just praised about the benefit of CDS. So that's the measurement he has made using JRuby. So JRuby is a pretty, it's basically a Ruby implementation written in Java. So it's a relatively large Java applications. And just focus at the bottom of the slide. So you see that Java 8.202, the startup time of JRuby is 853 milliseconds. And using Java 13 and CDS, 717 milliseconds. So that's a quite important benefits. The thing with CDS is that it's not something new. It's something that has been evolved through the years. So CDS has been introduced in Java 5. Back then it was quite limited. So first of all, it was only for the runtime classes, so the rt.jar. It was limited to the serial GC. But over the different Java releases, we have improved CDS. In Java 9, we have introduced application CDS. So before that, CDS was just limited to the class of the Java classes, basically not your own classes. In Java 9, you had the ability to use CDS for your own classes, but it was a commercial feature. In Java 10, that feature has been open source, so that means that it was free for everyone. In 12, we have improved, well, in 12, in 13, we have improved, we have continued to improve CDS. So now, for example, in Java 13, the way you create the archive for your own application is something that is very straightforward. You basically launch your application once, and your classes will be dumped automatically for you. Before that, it was a little bit more involved. You had an extra steps to do. So, outcome of this, please have a look at CDS. That's something that is in the platform since quite some time, and that's something that you need to rely on. We can go further than that if we want to reduce startup time. And for that, we might want to look at GraalVM. So GraalVM is an open source, high-performance polyglot virtual machine. It's a project that is run by Oracle Labs. It provides many capabilities, like the ability to do polyglot programming, so you can easily invoke, let's say, JavaScript from Java code, those kind of things. But one of the features that is particularly interesting in this context is the native image capability. The native image capability basically allows us to take a Java application and turn it into a native executable that will run on a target platform. The benefit of that are multiples. So it will reduce the startup time, because we don't have to first start the Java virtual machine. When we start our code, we basically start just a simple executable for that given platform. It will improve the memory footprint of that application, and it will also, and that's a side effect, reduce the size of our applications. So let's have a quick look at CDS, at Graal. For that, I'm going to leave that box. Let's see. So if I go here, I have my my simple application that I will first compile. No, sorry, I need to switch to a different version of Java for that. So MSQ. Yep. So Java minus version. So I'm using. Let's see. Yes, I'm using a Graal VM enable GDK. So let's compile that. So Java hello world, it runs. Now let's use Graal and turn that into a native executable. So what Graal is basically doing here, it looks at all the potential paths and it will create an executable. That's a quite expensive operation. So that's what this is done ahead of time. So this is a very trivial application, and you see that it takes like, I don't know, well, 33 seconds just for that. So if we look here, you now see that we have this hello world. If you look at the type of that file, it's a Mac, so it's a OS X executable. So let's run it. Oops, sorry. Hello world, and it's pretty fast. Let's try to time the execution of that guy. 10 milliseconds. Let's try to compare that. So the same execution, but this time we're going to run the bytecode. And well, you see it's fast, but from 10 milliseconds we went to 224 milliseconds. So basically 22 times slower. And also the thing is that if you look here, you see that basically this hello world executable only weighs 7 megabytes. And that's basically everything needed to run our code. So it has the Java bytecode, which has been natively compiled to Linux, well, to that target. But also it has, given that we're starting from Java code, our code expects to have some stuff provided by the virtual machine, like memory management, like possibly threading and so on. So in our in those 7 megabytes, we have a super lightweight virtual machine that is called Substrate VM. And that's all we need to run our application. So you see that by using Graal, we basically can greatly reduce the startup time of our Java code. Now, this doesn't come for free. There are a few limitations with Graal. So right now, Graal, for example, is only supporting Java 8. The Java 11 the next version of Graal VM will support Java 11, and it should, well, I've been told it should happen this month, so that's pretty imminent. There are other additional limitations, like, for example, if you are using reflection, it might be difficult to work with Graal. But anyway, if you can work around those limitations, well, you might want to look at Graal if the startup time, if the size of your Java application is something critical. And clearly, when we're talking about running Java into containers, that's something which we need to look at. Now, something which we have to keep in mind, we have Substrate VM, which is a lightweight VM. On the other side, we have Hotspot. Hotspot has been tuned for many years. So clearly, for example, the GC that we have for Graal in Substrate VM is not on par with the GC that we have with Hotspot. So if your application is long running, maybe it's a good idea to stick with Hotspot. If your application is ephemeral, so if your Java application will be invoked and die 10 seconds later, maybe Graal VM is a good solution. So next, our JVM should behave as a good citizen when it runs into containers. Why? So I'm not going to spend time on this slide because it's very busy, but the takeaway here is that basically from each release of Java, we are trying to make sure that Java, and namely the Java virtual machine, can work nicely into containers. And clearly, not everything is done yet. You see that we still have open tickets. But why we do that? We do that mostly for the ergonomics. So ergonomics is something that the JVM do since, I believe, Java 8. And the idea with ergonomics is that the JVM will basically, when it started, will look at a few metrics, namely, how many CPUs do I have and how many memory do I have. So if you don't specify anything, the JVM will try to auto-tune itself so that it provides a relatively good behavior. Now, let's go back to our example at the beginning. So let's see, we had Build minus t. It was minus q. You see the keyboard? I was not lying. So let's run that container. So msq. So that's the container that we started at the beginning. So now it sees that we have 3 cores. Why? Because my Docker is container only to use 3 of my 4 CPUs. Based on that, the ergonomics decide that given that the JVM has 3 cores, it will only use 2 cores for the command for join pools, and so on and so on. Now let's do this. I think it's CPU. No, sorry, not like that. And it's CPU. So let's now tell Docker to only use 1 CPU out of the 4 that I have. And well, you see that our virtual machine still sees 3 cores, and our phone join pools will be configured to 2. And effectively, we only have 1 CPUs. We can also do that for the memory. So let's pretend that we only have 32 megabytes available. So effectively, our container only has 32 megabytes, but you see that our JVM still has still thinks that it has 44 megabytes. Needless to say that that code, if it tries to run for more than a few seconds, will be killed by the container itself because it will just drain all the resources. How to solve that? It's very easy. So we just need to open JDK. We just need to use a recent version of the JDK. Let's build that again. Let's run that again. So 1 CPU, 32 megabytes of RAM. And this time, well, you see that the JVM inside the containers only see 1 CPU, so it will configure the command for join pool with 1 CPU. And the ergonomics will also configure the virtual machine that is available to the JVM itself. 15 megabytes, given that we only have 32 megabytes. And obviously, I can be a little bit more generous, and you will see that the JVM will adapt itself accordingly. So it sees 2 CPU. It will still only allocate 1 CPU for the command for join pool. But this time we have 32 megabytes for the JVM itself. And that's basically the ergonomics in action. And that's why it's important to use a recent version of the Java virtual machines. If you don't do that, the ergonomics will basically be screwed, and you can be sure that your code will be in very bad shape very quickly. So, wrap up. So we've discussed quickly some techniques that we can use to basically reduce the startup time of our Java containers at the container itself and at the application, at the Java layer itself. And we also discussed why it's important that the JVM behaves correctly when it runs within the containers. So some advice: whenever possible, use the latest Java version, and please never use java.-latest. This is a very old Docker image on Docker Hub that we are trying to get rid of, but it's still there. If you can't use the latest version of Java, at least you should rely on an actively supported version of the Java virtual machines. Try to use a custom Java runtime with JLink. We saw some of the benefits. Try to move all the startup costs to build phase, and then the rest is really container as usual. So you might have seen this suite. So the top 10 most popular Docker containers each contain at least 30 vulnerabilities. The good news is that Java is not there. The bad news is that we are not immune. This is something from last May, where basically Debian, which were building their own OpenJDK, I mean the source is there, so it's pretty easy to build. They had a GA release of a specific version of OpenJDK before it was even released. So my advice: choose your base image wisely. It's not because it's on Docker Hub that you can use it. And secure your base image. And my final advice: don't trust on someone else to secure your base image, regardless if you're using Java or not. This one is super secure. Okay, just on time. 000. So I believe we have a few minutes for questions.